Hello everyone. I'm Yannis. I'm a security engineer at Dedaub. And in case you haven't heard of us before, we're a security company who is heavily interested in program analysis, technology, and research. We have successfully conducted over 200 audits, and we have used our security expertise together with our program analysis tooling in order to disclose numerous vulnerabilities. Many of those have resulted in us receiving bounties, amassing a little bit over 3 million in total. So the point of today's talk is to give you a high-level overview of how a static analysis, in particular our static analysis, can be improved to be detecting real-world vulnerabilities. But why is that important? So I'm citing two papers here, both of which argue that publicly available tooling or automatic tooling in general only detects 20 to 30% of the vulnerabilities that it is supposed to be catching. The same papers also argue that those type of tooling generate many false positives, and this is something that discourages both the developers and the security engineers from using them. And these arguments perfectly capture the hard task that automatic tooling has to get right. You have to be precise, meaning that you have to be reporting true positives. Nobody likes false positives. But you also have to remain complete, because if you don't find real-world vulnerabilities, nobody takes much value out of your tool. And this is what I'll be talking about. I'll give you a high-level overview of our static analysis pipeline, and we'll look through a couple of real-world hacks and see what we can get out of them. So our analysis pipeline is based on previous research work, and I won't dive into it much, but essentially there are two parts that we need to talk about. The first one is GigaHorse, which is the backbone of our famous decompiler. And what GigaHorse does essentially is getting the EVM bytecode and lifting it to a normalized IR, intermediate representation. This brings back the notion of variables and statements, as you can see here. You don't have to memorize this. I'm just giving you I'm just showing you how variables and statements are brought back to life, essentially. And also, GigaHorse allows us to argue about the ordering of basic blocks. And it also allows us to talk about memory usage patterns. And this covers calls, this covers array pointers, and inferred struct pointers. And lastly, but not least, GigaHorse also tries to detect storage usage, and this can be used to infer the high-level storage layout of a contract without peeking into its source. The second part is Symbolic, which is our main analysis technology regarding vulnerability detection. And what Symbolic essentially tries to do is assign proper symbolic and concrete values to all those variables inside those basic blocks. And it does so by trying to be path sensitive, meaning that a variable will receive a value only if that value satisfies the constraints that make that point of the program reachable. So this is an example of the information we get out of Symbolic in our analysis. So it essentially says that variable A may have the concrete value 3 when the local variable is some sort of value that is provided by a checked address. This is why we refer to it as owner. And we know that the caller of that function at that moment is the owner itself. So what this essentially provides us with is a way to argue about context, execution context. So we assign symbolic and concrete values to the variables, and this allows us to argue about tainted or trusted input, and also allows us to argue about parts of the program being reachable only by a checked caller, the owner, or any user, which is essentially an untrusted user. So picking into what we actually write to get our vulnerability detectors, we implement all our parts of the analysis in Dedaub. You don't have to understand anything about Dedaub. A useful mental model for what I'm about to present is that all the data regarding program execution, the control flow, memory usage, and so on, is being inserted into tables, like those of a relational database. And a successful series of joins produces new tuples, which are inserted into new tables. And Dedaub is really nice because it allows us to run recursive queries on top of those tables, which is something you typically can't do with standard SQL. So the point I'm trying to make here is that, hey, Symbolic says that this variable under some execution context may have a value that is coming from an untrusted user, a user that is not checked. And that variable seems to be flowing, meaning that it's being assigned indirectly or directly to the argument of a call that is a transfer. And that argument is the first argument of the transfer. So essentially, all this is Dedaub stuff for trying to say that your receiver is tainted at this point. So I'll be guiding you through two real-world attacks that got us into thinking of how we can improve our detectors. Because as I said previously, static analysis is hard and it misses things. So we have to constantly be iterating on our tools and improving detection. And we have to do it in a general way and avoid producing too many false positives. So the first hack we're going to talk about is the sturdy finance one. So right around June last year, sturdy finance was hacked for around 800,000. And the root cause was they were directly reading from Balancer the spot price of a stable pool LP token. So it's perfectly fine to be doing that, but you have to be aware that the Balancer vault can be abused into producing inflated values because of a read-only reentrancy vulnerability. So I will not go through the code of sturdy and show you the Oracle code that read of Balancer, but we are interested here into how our analysis could be adapted into detecting the read-only vulnerability in the Balancer vault. So before diving in, this might remind you of the read-only issue that Chain Security had discovered on Curve, so a shout out to Chain Security. This snippet of code right here, you don't have to dive into it very much. You have to take notice that it's guarded by a reentrancy guard, and you have to know that it's called upon every deposit or withdrawal in a Balancer pool. So what those marked areas do, the red one will call into the pool, and your LP tokens will be burned or be minted to you. And then all token transfers are going to take place. The pinky one, is where the actual pool balances get updated. So this is what you have to keep in mind. Their LP tokens are minted, token transfers take place here, and this is where the pool balances are actually updated. So if we take a look at WETH withdrawals, so we're still on the red box right here, WETH withdrawals perform a callback back to the recipient, which makes sense, right? But at that point, we have to take note that the pink box has not executed yet. So the pool balances are not fully updated. And that means that even though the LP tokens will be burned, meaning that the total supply of those will be adjusted, and we will have received our funds, the pool doesn't know it yet, because the balances have not been updated yet. And that's the key idea behind the balancer's read-only reentrance, view-only reentrance. And as you can see here, the code that actually gets the exchange rates for those LP tokens will get the balances of the pool and attempt to divide it after going through the amplification parameter and invariant of the stable swap implementation. You don't have to worry about those, but you can think of it as those being divided. So since balances have not been updated yet, and the total supply has been reduced because we're within a withdrawal, the share price of the LP token is essentially inflated. And this is what happened in Sturdy Finance. The attacker inflated the price of his collateral, and that allowed him to borrow more than he should have been able. So, why is this interesting from a static analysis point of view? So, a reentrance guard is being used, even though the execution clearly is hijacked in the red box when we reach a native transfer. But what prevents us from flagging every view-only reentrancy in this world is that even though the state is inconsistent, meaning that there are some pending state updates that have not taken place, and our analysis can easily infer that the nested mapping at storage location 0x9 has a pending update because the store follows the native transfer. We cannot naively write a detector that looks for all reentrancy points and warns you about public functions that might read that storage location. And this is because, in practice, a lot of perfectly secure contracts break the check effects interaction pattern, but they're careful with how they use the reentrancy guards, and you have to keep in mind that public getters will be valid public functions that read those fields, and also do not have a reentrant guard. So a naive analysis will flag many contracts, and this is not suitable for us since we're targeting a low false positive ratio. So what is the heuristic that we might use to try and filter out some false positives? If we take a look at the view-only reentrancy of balancer, the storage location that we care about the pending update, is the one that stores the balances of the pools. So essentially, this is a really important storage location. If there was a way to filter out which locations are actually important, then we could argue about those and implement a detector with hopefully a low false positive rate. Oh. I think I broke it.
There's an arrow that appeared.
Oh, I cannot see it because of the sun.
Oh, you cannot see it because of the sun. Can you click again? Better?
No, I mean that the remote. Yeah.
I think we need to leave the presentation mode and return. How do we do? So exit and return. Try now.
Nice.
Oh, so let me. Okay, so back to our topic. We're trying to infer important storage locations. And this is the part where static analysis might help us, because the essence of a static analysis is that we try to approximate all program behaviors without actually executing it. And this, of course, causes some precision loss, and we cannot approximate all possible behaviors in practice, so we always give up on completeness or precision. But in this case, we can use the storage, the inferred storage usages in the contract to see, for example, that a storage location is being loaded, and that location then flows into a transfer. So this tells us that the storage location we just read from is a slot with monetary significance. So it is a sensitive one, and one we should care about. We can come up with many heuristics like the above. So for instance, we can talk about arguments of withdrawals or redemptions. All those arguments are monetary significant. So we could be flagging multiple storage locations. And this is what we do under the hood. So the final query-like snippet that actually detects, that will actually detect many view-only reentrances, but will not cause too many false positives, is this one. Looks like this one. So we identify a reentrant point when a reentrant signature is being called, or a native transfer is being performed. We take note of the storage ID that has not been updated when the execution is being hijacked. And in the end, we make sure that that storage ID has been previously been deemed as a significant one, with money significance. So you might be wondering, what do we mean when we say call to reentrant sign? Do we feed our analysis with all possible reentrant signatures? And the answer is no. We can run our analysis transitively on all deployed contracts, and this is what we do. So if we find an implementation of a signature that is reentrant, we mark it. The next time we encounter this call, we can argue if we have seen many implementations of this signature being reentrant. And this can propagate in a transitive manner, meaning that if I'm a reentrant implementation and I also I'm being called from another signature, then that signature is also possibly reentrant, and so on. So we can come up with a database of reentrant signatures, and this is because we analyze every deployed contract all the time. So we just wrote a detector, but in order to be sure that it is general enough, we have to be able to be detecting other view-only reentrances that have taken place in the past. And this is a compound v2 fork that has been mentioned today. It was called Paribus, and it was hacked for 70K on Arbitrum. And the thing to note here is that a transfer was being performed before the balance of the user was being updated. And in Compound, every market is a separate contract. So even though there is a reentrancy guard present, other contracts will query for the balance of the user, and the balance will not be updated. They will simply use a getter function, which is a view. It does not perform any mutations. So this is a modified example, but of the traditional view-only reentrance. And since we are detecting attacks like those, we can be sure that at least we have increased our completeness, which was the issue before. We weren't detecting any of those kinds of reentrances. And the final hack that we'll be talking about today involves Arcadia Finance. So just a few days apart last year, Arcadia Finance was hacked for around $500,000. And this time the reentrancy itself is not that impressive, because they could have used they could have used the reentrancy lock and prevent everything, but the fact that they didn't use one allowed a user to liquidate its vault at an unexpected place, and this bypassed a few withdrawal checks that we'll take a look at right here. So for Arcadia Finance, it's a protocol that lets you lend and borrow funds. And in order to do so, you have to have a margin account. A margin account is materialized into a vault contract that is being deployed for you by the protocol, and you are assigned the owner of that contract. So you have a vault contract. You deposit funds into it, and then you can use other parts of the protocol code in order to borrow funds. Before checking the code, vaults seem a bit like wallets, right? So you have to be able to interact with other on-chain entities. And in order to accommodate that, Arcadia allowed for permitted action handlers to be called. So if we take a look at the code without messing with the details a lot, we can see that the user may provide an action handler. The action handler address is being checked because the protocol cannot trust you blindly to be calling into things. And then you're allowed to set up the state before performing the external call. So you may transfer some funds into your action handler. And then your action handler would be called. And after execution is returned back to the vault contract, the vault will perform health checks. So if you have used your vault to previously borrow funds using your collateral, then your debt cannot be larger than your collateral because the protocol would have bad debt. So the thing to note here is that funds are being transferred to the action handler. The action handler will be called, and afterwards, all the checks regarding the health will take place. So the attacker took notice that the protocol allowed for an action handler that basically implements multi-call. So you can call into any address you want, and you can provide any call data you like. So this, even though it is checked that it is allowed from the protocol, can be turned into a reentrant call pretty easily. And what the attacker did is, after transferring all funds to the action handler, it had the action handler transfer all funds into an attack contract and call into it. So at this point, the attack contract could call back on the vault, because if you take note, there are no guards present anywhere. So what the attack contract did is called into liquidate vault. So this function essentially liquidates the vault. The liquidation check will pass because if you take notice, all collateral has been sent away. We have only debt inside the vault when we're inside the reentrant callback. And so this will set up a few variables, namely fixed liquidation costs and is trusted the creditor set, which will cause the check after the action is performed to be skipped altogether. So the health check after the action handler returns is skipped here because fixed liquidation cost has been set to 0, and when is trusted creditor set is false, get used margin essentially says you have not borrowed anything. So the check is skipped altogether. So at this point, the attacker could have borrowed using his margin account and get away with all his collateral. So why is this attack interesting again from a static analysis point of view? If you take note, all this time, the person attacking the contract is someone who is regarded as the potential owner of the contract, or at least a trusted address. So many static analyses try to argue about whether the caller is checked. At this time, the caller is checked, but we still have in our hands an exploit. So how could our detectors be adapted into detecting attacks like those, where the caller is checked, but for some reason he still performs malicious actions? And the heuristic we can come up with is the notion of partial ownership. So even though the caller is checked, and on theory he shouldn't be incentivized to exploit it, we can take note that his actions are not completely free. So we have instances where, even though this is the owner calling the contract, his inputs are heavily sanitized, and those can serve as hints that even though this is the owner of the contract calling, he essentially is somewhat restricted, so it's like he does not fully own the contract. It's like the contract has been deployed for him, which was essentially what Arcadia Finance was doing. It was deploying a contract for its user. So if we take this notion and incorporate it into an example query, we can see that, okay, we'll continue looking for reentrant points, but this time, if we take notice that the address of the callback is being sanitized by an external call, and that external call also controls money-sensitive operations, then we'll warn about it, even though the code is being reached by a trusted caller. So at this point, again, you might wonder what I mean by a sensitive operation. And this is where the paradigm of us analyzing every deployed contract comes back into play. So if we take note that a signature in general is implemented in a way that reads an argument and then performs a transfer or a withdrawal, and somebody else is using that signature, another function implementation, and we run statistics on those implementations, we can again come up with a database that says, hey, look, those signatures have been involved with withdrawals, transfers, and in general, money-sensitive operations. So our database, let's say, has a lot of signatures that seem to us like money-sensitive operations. And this detector, again, sorry. So this detector should be, in theory, complete. All we care about, other than this, is the false positive ratio, again. And as we try to do with all our detectors, we have to generalize them. Otherwise, they're not really practical. People don't get much value out of them. And a way to generalize partial ownership is to think that every instance of a unique sanitization being performed is actually a candidate witness of partial ownership. What I mean by that is that if we, again, use the fact that static analysis tries to argue about the entire program behavior, if we take note that there are many sensitive operations that are only reachable by an owner, but are checked either by an external call or an if statement or a require or anything like that. If we count those numbers, that number of instances, it can give us a pretty good metric of whether this contract is actually partially owned or not. And this is actually code from another project, the Standard IO project, which, as you can see, only allowed for the minting of some tokens and the removal of collateral when the partially owned contract was fully collateralized. We don't have to dig into the details of what does it mean. But essentially, even though the protocol gave the user a contract, he was not the full owner of it. He was restricted in many ways. And if we incorporate the number of unique sanitization checks throughout the entire contract into a new detector, like this one, then we will be easily able to detect that even though only the owner of the contract can reach this completely unprotected swap, we now know that the owner is incentivized to practically drain the contract, because we've seen instances where he's really restricted on the sensitive operations. So we can raise a warning about this, and it would have been a true positive, but as with other hacks in this presentation, we had to reiterate on our detectors. So hopefully in the future, we might be able to detect partial ownership issues sooner. So that was for me. Thank you for your attention, and a big thanks to the organization of this event. Yes?
I have a question regarding the notation that you used for the curves. That looks a lot like Prolog or something.
Yeah.
Is it actually how it's implemented, or is it just some syntax that you use to make it?
No. The syntax is actually the syntax of Dedaub. But while Prolog does a search, Dedaub is bottom-up, meaning that you provide it with some facts, and it can provide you with some polynomial runtime guarantees that it will figure out everything it can. Of course, we break that polynomial guarantee because for some other detectors, and in general throughout the analysis, we produce new tuples. So this is a non-monotonic computation, and it breaks the polynomial guarantee. But being able to run on every single deployed smart contract is a priority for us. So we try to optimize for it.
I think it's a very cool natural syntax to define like the custom detectors.
Yeah.
I really like that part.
Yeah. You also come from a formal verification background, so to you it is a pretty natural way of thinking stuff. Conditions and inferences, pretty much.
Probably
Yes.
a stupid question, but so you flag that in a contract, some address
Okay.
is a privileged user because they are allowed to do some stuff, but also not completely privileged because they are denied from doing some stuff.
Yeah, that's the concept of the partial ownership.
Partial owner.
Yeah.
And when you see that someone is a partial owner, then you try to flag potential behavior where this
Yeah.
owner might actually be incentivized to join.
Yeah, so if this wasn't an owner to begin with, we would be flagging it pretty easily because it is an untrusted caller. But now we have to be cautious of.
So here's my question. In the end, wouldn't you achieve the same thing by simply seeing that a user that was denied, if this user went through this route, he would be denied?
Yeah, we know that.
Right?
Yeah.
But it exists another route to do this. And this would be a formal proof that there is a problem here.
Yeah, but the thing to note about those attacks is that there is no other person that can be pulling those, only the owner. You're talking about the Arcadia hack, right?
Yeah,
Where
yeah,
the.
yeah.
Oops, sorry.
Can you go back to the picture? Yeah,
This one?
oh, no, sorry, not this one. Yeah,
Uh,
okay.
Yeah. Yeah, you're talking about this instance, right? So this comes back to how our analysis technology works. Our analysis can argue about a checked or an unchecked user. So all checked users essentially collapse into one user. So for us, all those users are one, a trusted user.
Okay,
Yeah. The owner, it's being noted as the owner, but essentially it means that it is a checked address. Yeah. Yes.
You mentioned you are checking these detectors.
Yeah, this is part of our internal tooling that people may actually register to be using. You can also sign up for a free trial, but the developer tier allows you to be uploading your code only. If you go up the tiers, we'll expose you to our internal tooling that allows you to type any address or search for any warning and get a list of contracts that have been flagged with that particular issue. So this highlights why it is really important to be trimming false positives, because if that database is being polluted with false positives, it actually serves no practical purpose. So I think